We cover quite a bit of topics in this lecture. It's called standing waves. And the concept behind a standing wave is sort of visually shown here. If we have a waveform that basically has it's a fixed point, and it could have points where it appears the particles are vibrating in place, and parts where the particles are vibrating at sort of a maximum, then we could have a standing wave created. So this pattern below is a standing wave pattern. So it is when we have stationary interference, a stationary interference pattern of successive nodes and antinodes, and we'll talk about what those mean. And it's created when waves traveling in opposite directions have the same frequency, amplitude, and wavelength. A node is a point where we have where we're generally at the equilibrium point of a wave. So for this standing wave pattern where we have these three loops, the nodes are in between the loops. They are periods where we have destructive interference. Essentially, the particles that are vibrating in the wave are at rest. The antinodes are where we have a maximum displacement, either a crest or a trough occurring, or alternating crests and troughs. So these antinodes are areas of constructive interference. They're the areas of maximum constructive interference in the standing wave pattern. This sketch here shows three different standing wave patterns, and we're asked to label the areas of the nodes and the antinodes, so I'll just kind of talk through it here. A is our antinode, so this is an antinode part. It's at the center of the single loop. The N is at the end, at the fixed point. Here on this wave pattern, we have A's at the top, antinodes at the top of the loops. The nodes are in between those loops and at the end. And again, antinodes at the top of the loops, nodes between the loops. For complete destructive interference to occur, what must be true of the frequencies, wavelengths, and amplitudes of the two waves? So if the frequencies, wavelengths, and the amplitudes of the waves, so here we have this wave that's generated by the hand and this wave that's generated in response, if those are the same, the frequency, wavelength, and amplitude, then we can have a standing wave pattern created. In a standing wave, what constitutes a wavelength and what constitutes half a wavelength? So let's look at the first standing wave here. This would be half of the wavelength. This is only one part of the upper portion of the wave, and then this is the lower portion. And for this one, we would have a wave being up and down, and then another waveform being up and down. And for the next one, up, down. That's one waveform. So essentially each loop is half a wavelength. We can use the universal wave equation to determine the speed or the frequency. So you can usually read the wavelength, you might be able to read the wavelength from the wave and then use the universal wave equation to determine other parameters. So for this question, I won't show you sketches. You can draw the sketches on your own, but we can talk through this. Each loop would have to be a half wavelength. So in the first case, and again, we have a 6-foot rope, so it's attached to the wall at one end. So in the first case, half a wavelength for 12 would be 6 meters. So the entire standing wave pattern would be a single loop. For the second case, B, divide that by 2 and you have 3 meters. So that's our half wavelength, that's our loop it would be one single loop. Sorry, two loops. One loop for with a half wavelength of 3 meters, and then another loop with the other half wavelength of 3 meters. The last one, in order to have 3 meters, well, each loop would represent 1.5, so that would be 4 loops shown on that rope, that standing wave pattern. This question says the distance between two successive nodes in a vibrating string is 10 centimeters. The frequency of the source is 30 hertz. What is the wavelength? So to start with this question, we need to find out what the wavelength is, and they've told it to us, but we have to kind of use our understanding of standing wave patterns. So it's a standing wave pattern, and it says the distance between two successive nodes, or basically the length of one loop, is 10 centimeters. So that's a half wavelength. If we multiply that by 2, we get a wavelength of 20 centimeters. What is the speed? Well, now that we know the wavelength, to find the speed, we can use our universal wave equation. V equals lambda times our f, and lambda in this case is 20 centimeters. F is 30. So 20 times 30 would get us to 600, and we can write that in centimeters per second. Question number 3. Standing waves are produced in a string by a source with a frequency of 10 hertz. The distance between the third and the sixth node is 56 centimeters. What is the wavelength? Okay, the distance between the third and the sixth node. So how many loops does that cover? From 3 to 4 is 1, 4 to 5 makes it 2, 5 to 6 makes it 3. So that's 1.5 wavelengths. So the distance for 1.5 wavelengths is 54 centimeters. 54 divided by 1.5 gets us to 36 centimeters. That's our wavelength. So it's a bit tricky to understand that. Now that we know that our wavelength is 36, we can use the universal wave equation. 36 times 36 centimeters for wavelength times our f, which is 10 hertz, so we get 360 centimeters per second. The frequency of the wave that produces the simplest standing wave is called the fundamental frequency. It's also called the first harmonic, and it's given the symbol F0 or F0. This occurs when the shortest length of string L is equal to 1/2 of the wavelength, lambda over 2, where lambda is the wavelength. That picture shows visually what we're talking about there, where L is half the wavelength, and that is also represented by F0. So the fundamental frequency, it is the frequency that produces the simplest standing wave. It's one loop. It occurs when length of the string is half lambda. It's also known as the first harmonic. All standing waves after this require frequencies that are whole number multiples of the fundamental frequency as well, just to state that again. The additional standing wave frequencies are called harmonics. Harmonics consist of the fundamental frequency, or the first harmonic, of a musical sound, as well as the frequencies that are whole number multiples of the fundamental frequency. When a string vibrates with more than one frequency, the resulting sounds are called overtones. So this is an important chart to copy down. Your symbols are F0, but the names of them are a little bit different. So F0 in the first case is your first harmonic. It's called your fundamental overtone. And then for one loop, for 2 loops, we have F1. That's your second harmonic, and musically it's called the first overtone. If we have a vibrating string, we're kind of getting back to music here and sound. There are standing waves, but there's also different patterns that, or different parameters we can adjust to make different sounds. And the frequency is determined by 4 factors: the length, tension, diameter, and density of the string. When a piano is made, it is theoretically possible to obtain the range of frequencies necessary by just altering the length of the strings. However, this would be absurd because the shortest string would be a meter and the longest string would be 150 meters. So you can make a piano that large to get all of the sounds of the piano, but that would be just by altering the length. That's why we alter other things like the density and the tension. This is a multiple equation here for the frequency of a vibrating string. And it's a series of comparison ratios here. So F1 over F2, the comparison of the frequencies, the ratio of the frequencies is equal to the reciprocal ratio of their lengths, or the square root of the tension, or the ratio of the tension, or the reciprocal ratio of the diameter, or the reciprocal ratio of the square root of the density. All of those represent different equations. Let's try something here. It says, question 4, the string of a violin is 30 centimeters long and has a natural frequency of 288 hertz. Where must the violinist place his finger or her finger to produce a B note with that frequency? So we have to find one of our F1 over F2 equations here. And this case, we're dealing with length. So let's go back and look. Length, it's the reciprocal, so it's L2 over L1. So we start with this. And if we want to find out what our L2 is, then we rewrite it as L1 equals F1 times F2. L2 equals L1 times F1 over F2. So this is 30 centimeters, 0.300, times F1, which is 288 over 384. So we have 0.225, or L2 is 22.5 centimeters. And we could have just not converted it, which I think I'll do for the next problem. Next we have a piano string with a pitch of A is under a tension of 140. And we are asked what tension would be required to produce a high C. Okay, so this time we are comparing our frequency, which is F1 over F2, with our tension, which is the square root of T1 over T2. So for 5, we have F1 over F2 equals the square root of T1 over square root of T2. I need to rearrange for T2, so I get T1 F2 over F1, and then I square both, squared. So T2 equals T1, which is 140, F2, which is 523 over 440, and I square that. And let's turn my calculator on. We have 140 times 523 squared divided by 440 squared equals, that's going to round to 200 newtons. Okay, let's work on the next problem. Two strings have the same diameter, length, and tension. One is made of brass, so it has a different density than the other, which made of steel. If the frequency of the brass string is 440 Hertz, what is the frequency of the steel string to 3 significant digits? Okay, let's look at the comparison for density. If we go back up to our multi-equation here, it's the square root of D2 over the square root of D1. So square root of D2 over the square root of D1. I need to solve for frequency 2 in this case. So F2 equals F1 times the square root of D1 over the square root of D2. F1 is 440 in this case. Square root of D2, which is, D1, which in this case would be the brass string, so that's 8700 over the square root of 7830. Okay, let's do this on our calculator. So one way of doing this is we can just do the division, 8700 divided by 7830, and then find the square root of it, and then multiply this by 440. And we get 463 Hertz. And we have one more question to do in this lecture. They say 464. You know what? I didn't round it properly. It is 464. So I've just changed it. Note that it's 3, if you look back at the calculator here, it's 463.8. State what would happen to the frequency of a vibrating string if there is a full 4-fold increase in the string's length. So tension, diameter, and density. You can try this on your own and just see some of the comparisons. Because we have these proportionalities, you can see that sometimes it'll change with the at a ratio that is to the square of the parameter. Sometimes it'll be the reciprocal or inverse proportional. Sometimes it'll inverse proportional to the square.